So if you have to pick up your homework, you can get it at the end of the class. Graded homework. So there's an assignment due today, and there'll be another one posted soon. Just to remind you, I have my office hours now scheduled on Mondays from 10 to 11. Okay, so we'll be in room 30 to be the last time. And I'll look at your schedules. Gopi said he's available all afternoon today, so we'll see. We won't have office hours all afternoon today, but we'll find an hour that hopefully matches everything. Okay? For the last little test. All right? So, let's review what we talked about last time, because lots of people stayed under their covers when it was cool last Thursday.
I got forwarded to the small
that's forever on YouTube. In 2035, people will know that Zeke went. All right. So what we're talking about are hydrogenic atoms. We'll talk more specifically about hydrogen, but as we discussed, the same exact formalism describes all such systems that are the interactions between two oppositely charged point particles. So that's hydrogen, positronium, very highly ionized cesium with one electron, any such system with two oppositely charged point particles, what we call hydrogenic atoms, okay? And as we discussed, this is the approximate Hamiltonian when we neglect relativistic effects. So we'll come back to that soon. But the dominant force here is the electric field, or the electrostatic force that is attracting these two particles to one another, okay? And under that approximation, we can simply write down the Hamiltonian. And as we discussed, this is not separable in the degrees of freedom associated with the positive and negatively charged particles. They're interacting, so they're coupled together. But if we change our degrees of freedom to talking about the center of mass and relative coordinate degrees of freedom, then the Hamiltonian is separable. Okay? And the center of mass, Hamiltonian is a free particle. We generally ignore that for the moment. And then the relative coordinate is just the motion of the relative mass, that is to say the reduced mass, in a central potential that falls off like the one with the distance to the first power. Okay? So because the Hamiltonian is separable, that means that the eigenstates of the Hamiltonian, we can find eigenstates of the Hamiltonian that are separable, that are product states, okay? And so the total energy of the system for given this kind of energy eigenstate is the sum of the energy of the center of mass, which in this case would be the free particle energy of the center of mass of the atom, and the relative coordinate energy. Okay? So we're looking then at solutions to the relative coordinate state time-independent Schrodinger equation. And that has this simple form. And R here is equal to the magnitude of the relative coordinate. It's the distance the relative distance between the two particles. And this Hamiltonian is rotationally symmetric. Okay? And because it's rotationally symmetric, it's isotropic, it's spherically symmetric, that means that we know that we can look for eigenstates of the Hamiltonian that separate into eigenstates of L squared and LZ, both of which commute with the Hamiltonian. And then what's left over is the radial component. Okay? So we write the kinetic energy of the system in terms of radial motion and angular motion. And with this ansatz for our state, the Hamiltonian has this form for a given value of L. Okay? This is the radial equation. So when you have a spherically symmetric potential, the whole story then comes down to solving the radial equation. That's what you have to do. All right? So again, in the position representation, our wave functions have the form, the angular dependence is known. That's the YLMs. Those are the eigenstates in the position representation, the spherical harmonics. And then we have the unknown radial wave function. And we can solve this most simply by re-expressing the radial wave function in terms of what's known as, we discussed, the reduced radial wave function. Which factors out this factor of 1 over r, because when we do that, then the radial equation takes a simple form that looks like a 1D Schrodinger equation, right? Which is, this looks like the usual kinetic energy term, and angular momentum, and an angular momentum barrier, and then whatever the potential is, in this case, our Coulomb potential. Okay, and this is written for the case of hydrogen, where we have a proton and electron, both of which have the same magnitude of their charge. The center of mass is almost completely at the proton. The electron has such a puny mass compared to the proton that the total mass is almost all the proton mass, and the reduced mass is almost completely the electron mass. Okay? So in that case, it is kind of separable, because inseparable in the coordinates of the proton and the coordinates of the electron, because basically the proton is the center of mass and the electron is relative to the proton. It's a very good approximation. All right. Now, again, I want to re-emphasize, because this is so important, this notion of dimensional analysis and extracting scales. So probably you're working on that in your homework if you haven't already completed that. But I just want to re-emphasize this. When you're seeing a problem for the first time, the first thing to do is to identify the scales, the physical scales of the problem. And then define everything in terms of those physical scales, and then everything is dimensionless, okay? So we have, in this case, this equation is characterized by 3 fundamental constants. We have the electron charge E for its magnitude, we have h bar, and the mass of the electron, okay? And then the question is, how do you make characteristic scales? I mean, it's just really dimensional analysis. There's a number of ways that you can look at this. Firstly, we can say what we want to get are the characteristic scales some characteristic length and energy. Okay. We call this thing A naught, we call this thing E naught, right? So if I look at this, I can see that there is, if I have a charge, then there is a clear relationship between charge, length, and energy, right? What is that relationship?
Charge squared divided by length is energy.
That's right, in CGS units, right? If it was in SI units, there would be a little 4 factors. Well, not out here, right? That's the potential energy that associated with some charges, right? And that we'll just define as E naught. So this gives a clear relationship between energy and length, okay?
Which you get from the potential energy.
Which I get from potential. There's another relationship, right? Because right now, there's only one equation, there's 2 unknowns. But there's another way we can get energy out of the system based just on h bar and m. And that's kinetic energy, right? So kinetic energy, how do you relate kinetic energy to h bar, m, and length?
Could you
Or
just like,
squared over.
Well, hold it, see, go ahead. No, please. Just,
well, I was thinking like, maybe this is roundabout, but I would look at like, you know, h times frequency, like maybe de Broglie wavelength. I don't know if that would be
Sure.
roundabout, but
Yeah.
I would probably get there.
You
but,
could get there.
Yeah.
But to do that, it's a little bit complicated because you don't know what energy. Frequency is related to energy. And we don't know energy.
Okay.
Right? Yeah. I mean, that'll get there, right? So how else might you go about it?
You could look at the first term in the Hamiltonian, just h bar squared divided by m divided by length squared.
Right. So that's another way, it's another way of saying it is the following. So this is sort of potential energy. There's kinetic energy. Kinetic energy is p squared over m. Right? But how is p related to length?
Could you do like, put it like in the position representation and check out the units there?
You could.
Okay.
Yeah. And that will get you there. But if you just want to just sort of get just quickly, we know the uncertainty principle, right? There's a relationship always between this event and de Broglie wavelength. That's the right idea. There's a relationship, given a length, there's a characteristic momentum. Because momentum is h bar over length. Right? So that's, I mean, that you could get a visual representation, yeah, do it formally, but this is the kind of thing a physicist should know. So that's h bar over the length squared over m, which is exactly as Keith was suggesting. And we should call this E naught as well.
The a naught squared.
Yes, thank you. Right? So there are 2 equations, 2 unknowns, and so we get from this the characteristic length is h bar squared over the mass of the electron e squared, and the characteristic energy is me to the 4th over h bar squared. Now you could have gotten there by trying to write down kilograms, meters, so whatever, and you get it eventually, but this is the kind of sort of, you know, between your fingertips argument you should familiarize yourself with. And this basically tells us what these are characteristic units, or what are called atomic units. Okay, this is the Bohr radius, and it's about 1/2 of an angstrom, and this is what's known as a Hartree, which is 27.2 electron volts. Yeah.
When you change things like the charge of one of the particles, how does that impact the...
Oh, it does?
Yeah,
Because
it just seems less obvious, because some of the parameters
Yeah.
have only odd powers of e.
Sure, so it doesn't change them in obvious ways. You have to kind of look, yeah. So we'll have more chance to
Look
look
at
at.
that equation over there.
Yeah,
So basically, do you replace n by nu and e by q minus q plus?
or the
e squared
plus,
by
you have the plus. So now we have q plus
q.
times q minus, right? And this would be the reduced mass.
So the trick is the same. Right?
It's exactly the same. So there's a kinetic energy and a potential energy, and then you would set them equal. Yeah.
But in one of them, I got an odd number of powers of E. So I don't know which, so when it's an E squared, I could put it in the charge of one times the charge of the other. But when there's an odd number of powers of E, I didn't know what, which one
I
to
have
use.
to look at
for
the
the-
specific
Yeah, but
situation you're looking at. I mean, of course, these are all about scales. Nothing is exact here. But this trick, I mean, I can, you know, so if I went through and, you know, as we said, if I went to took this equation and factored out the characteristic units and then just tried to get rid of anything in this equation, there's never going to be questions of, you know, the status of 2. Those are kind of your choice, how you want to define them, but it won't affect in any way what the over, you know, the base, you know, how many powers of you have. Yeah,
I'm sorry, I'm confused. Well, how did you get odd powers
Yeah.
of 2?
yeah. I don't want to get into the
Okay, I'm
details
sorry,
of
I'm sorry.
homework
Okay.
here.
Okay, I'm sorry. Okay, I was
we have
really
other things to do,
This is-
but
An easier way to work through this in.
I don't want to talk about this right now. Okay, thank you. This is your homework. We'll discuss that there. Thank you. So let us continue on this. All right. So once I have these units, as I say, these are the units that define the atom. And so without solving anything, you know, you kind of know what to expect. The atom should have about this size, and the bonding energy is about that size. So that's a kind of good physics everyone should be able to do. All right, so with that said, we've been looking at this equation, and we want to solve here for the bound states. So if I look, as we discussed, there is the effective potential here, which is the true potential plus the angular momentum barrier. Which would have, you know, 1 over r potential for the Coulomb interaction, and then a 1 over r squared potential for anything that has some angular momentum. And so generally, the effective potential will be of this form, and this has bound states. If I call for E relative less than 0, since we've chose the 0 of energy to be 0 at infinity, the 0 potential energy. And then for E relative greater than 0, this is unbound states. Those unbound states are the states where the two electron, or the electron, say, and the proton are scattering from one another. So these will come back to later in the semester when we talk about everyone's favorite subject, scattering. But right now, we're talking about the bound states, okay? So what we said is we're defining the relative coordinate in this case as minus E binding, okay? So this is a positive number, which we call the binding energy. All right, so with that said, in dimensionless units, if I define the dimensionless position and the dimensionless energy, binding energy, then, and I really should redefine, because of course the radial coordinate has, the radial wave function has units. It has units of 1 over the square root of length. So I really should define a dimensionless wave function to get rid of that. And that, that doesn't appear here anywhere. All right, so that's my dimensionless radial wave function, then I have the dimensionless radial equation. All right? So I've gotten rid of all the units, and that's what I have to solve. Now, one thing again to re-emphasize what we discussed last time, and we have discussed last semester, are certain parts of the asymptotics. So the radial wave function, or the reduced radial wave function, u L of r goes like r to the L plus 1 as r goes to 0. That is in order so it doesn't, so it is a normalizable solution. That's an important thing to remember, okay? What it means is that we can always think about the radial wave function as having an effective infinite barrier, no matter what. Even if I had a case where I had 0 angular momentum and there was no barrier, it cannot, it has to go to 0 at the origin, okay? So it's like there's a infinite wall at the origin and only on the half plane from 0 to r. Of course, the true radial wave function, which is u over r, goes like r to the L, okay? And that means that for L equals 0 states, this is a constant at the origin, right? I mean, that makes sense because, again, remember, think about physics here, not just the math. What does it mean for a particle to have 0 angular momentum on a trajectory? It means that it's head-on collision, right? So the angular, classically we have this thing, it's going on an orbit of some kind. This has finite angular momentum. It has both radial and angular momentum. Whereas if I have a case where I go through the center of the sun like this has L equals 0. So there's a lot of probability for the particle to be right at the origin, which is where the relative coordinate is 0. Okay, it's important to keep that physics in mind when we're thinking about this, that L equals 0 states are states where there's very strong, there's going to be generally much stronger interaction than higher L states, okay? So we typically would expect in a problem like this that the L equals 0 states are much more deeply bound than states with L not equal 0. They're generally not degenerate. We'll come back to that for hydrogen. It's a little funky shape. All right, so the other thing we showed last time is that as r goes to infinity, this thing went like e to the minus kappa r, where kappa squared was twice the binding energy. Okay? We showed that last time. So with all of this, what we made the ansatz, we said that the radial wave function, we factored out the asymptotic behavior at small r and the asymptotic behavior at large r, and whatever is left out is some function. And this function f is constant as r goes to 0 and r goes to infinity. Or in other words, or another way of saying this asymptotic behavior can't be wrong, right? So it can't blow up any faster than that. Could be a constant. It's not quite true, but we'll see it is. Goes to 0 and doesn't blow up faster than either the capital R or as fast as, right? Otherwise, it would cancel this asymptotic behavior. Okay? And this is going to be the key to the fact that, as we know, we have bound states. That's to say, there is a boundary condition over here that will say that only when the curvature of the wave function is just right can it go to infinity. I mean, go to 0 at infinity and not blow up, just like we know in a, a square root or something like that that we do in 1D. All right? So, all right, now I gotta get my notes because this is stuff I don't remember off the top of my head. I don't want to fiddle around with algebra on the board. Let's see what we got here. Great. Okay, so we plug this ansatz, this assumed form, into our dimensionless radial wave equation, and we get the following. R bar, the second derivative of f with respect to R bar, plus 2L plus 2 minus 2 kappa R bar times the first derivative, plus 2 times 1 minus kappa L plus 1 f has to equal 0. Okay, that's just plugging in that ansatz into the radial equation. And this equation has to satisfy these boundary conditions. Okay? Now, there's lots of ways to go about it. Let me just remind you of one simple way. We can solve this based on the putting in a power series for f. Okay? It's a quick and dirty way to do it. So let's assume that this is an analytic function that we can expand around the origin in a Taylor series. So we take f to be some power series. Okay. And now we plug this into this equation. And then we can collect all the terms. You have to, since this thing has to be 0 for arbitrary r, that means every term in the power series has to be 0. Okay? So that's what we do. So what do we get? So the first derivative of this thing, well, and that's easy. The first derivative, j r bar to the j minus 1. And since this vanishes for j equals 0, it's equivalent to add plus 1, aj plus 1, r to the j. Okay? Yeah?
Why do we need to use a Frobenius series?
Oh, God, you got me.
Because it's fun.
Have to, I'm not sure there are not other ways that we can do, but certainly under the assumption that this converges, means analytic in this way, it is a correct expansion. Are there other expansions? Perhaps, but I don't believe, it's crucial to the solution that we have to use it this way, but we get the solution this way. All right, so we have the first derivative here. We take the second derivative. Do it again.
So is first sum be from 1? From j?
No, because the 0 term.
I see, yeah.
Yep. Right. So this second derivative, take this derivative again. I have j times j minus 1, aj r bar to the j minus 2. And I need to then look at r bar times that from this piece of the solution that, or piece of the equation that I see. So that is that. And then I do the same trick here. The j equals 0 term vanishes. So I start from j equals 1 and then shift. So that becomes j plus 1 times j, aj plus 1, r bar to the j. Okay? So now I plug this and this and this into this. And then, as I say, I can just equate them term by term. That is to say, every coefficient that goes like r to the j must vanish. All right? And I get the following solution. J times j plus 1 and j plus 1, that comes from this term, plus 2l plus 2 times j plus 1 and j plus 1. Oops, excuse me, let me just make this more clearly. Minus 2 kappa j aj plus 2 times 1 minus kappa times l plus 1 aj equals 0. Okay. And so from that, what we end up with is the following. That there is a recursion relation which tells me that the coefficient aj plus 1 is related to the coefficient aj through this equation. Okay? That's just what you get. All right, fine. So now the key is the boundary condition. Because without the boundary condition, we don't have uniquely defined the solution. The boundary condition is this. Okay? So, we are automatically satisfied with the boundary condition near the origin.
Should you change the sums on for the derivative of j equals 0 to j equals 1 and 2?
You would, but you see, I could do this one at a time. In this case, firstly, this starts at j equals 1, right? Because the j equals 0 term is 0. Now I shift everything down by 1, and that takes me back to j equals 0. That's how it worked. Yeah, but you're right. You have to be careful about that. But I did that very quickly and put it under my sleeve.
And you switched one back when you were writing it out. The second term?
Yeah, there are both
Both of
those
those
terms. Yeah, I'm going back and forth. Yeah. This is tedious and boring. I don't want to get into it. It's not the point. It's a little bit of algebra.
So this doesn't collapse into some tiny function named after some European?
It does.
Oh, okay, okay.
Yeah. Yeah, it's all about the 19th century. But we'll get there. It's la guerre, my friend.
Ah, okay.
Association, right?
Yeah.
Ah.
You should know this. 'Cause
Well,
you
that's what I was
probably
thinking, but I was like,
all
well,
study this.
I figured, but I thought maybe because you were rederiving it, it was just going to stop there, and then that was going to be it.
No, it's not it. So, right. So, how do we get there? Well, so now we have the asymptotic behavior. Okay, so let's look at this when J gets very, very large. Okay, because we want to know what happens to the power series when we start getting to large powers. Like that. So for J getting very large, we have the asymptotic behavior that this thing, well, all these guys, we have a J squared down here, we have a J up here, so this goes like to, we keep J, a J, right? When J is huge compared to L plus 1 or anything like that. And so this recursion relation tells me that AJ goes like, for J large, goes like 2 kappa to the power J over J factorial. That's just doing the recursion. Okay? Now, if that kept going forever, well, that means this is a power series we know. That's the exponential. So this would go like e to the plus 2 kappa r bar, right? It would blow up like that, and it can't. So what that tells us is that this power series has to terminate. It has to be a finite power series rather than an infinite series. Because if it was infinite, it would blow up in just the wrong way. Okay? So that tells us that the power series terminates. That means that there is a maximum value of J in this integral. It doesn't go to infinity. It has to go to some J max. Then we can satisfy the boundary conditions. And that J max we call n sub r. This is the radial quantum number. Okay? Why am I calling it the radial quantum number? Because it tells me the order of the polynomial of the radial wave function. It tells me how many radial nodes there are, right? If n sub r is 0, it's a constant. If n sub r is 1, it's got 1 node. So this is the number of radial nodes. All right. So, what that then tells us is that a n sub r plus 1 has to be 0. Okay? So, with that, plugging that tells me that this has got to be 0, where this is the a sub n. That tells me that kappa times that numerator, J max, n sub r plus L plus 1 times 2. Oops, sorry. No, that 2 is this equals 0, so that cancels out. Minus 1 is 0. So, that tells me that n sub r is equal to 1 over kappa minus L plus 1. Or that kappa is 1 over n sub r plus L plus 1. Now kappa was what we call the binding energy in units of 2. So this is equal to the square root of twice the binding energy. And thus we have solved it. The binding energy of the eigenstates of the hydrogenic atom are functions of these 3 quantum numbers, or in this case, it's also a function of m. Of course, it doesn't depend, the energy doesn't depend on m. And that binding energy is equal to 1 over 2 n sub r plus L plus 1 squared. Yes, Steve?
So is the binding energy dimensionless in the CGS? Is that?
No, not in CGS, it's dimensionless in the fact that we've taken out the units, right? This is the binding energy, this is the dimensionless binding energy,
Okay, okay.
right?
Okay, thanks.
So the actual binding energy, or the energy N sub R, L, and N, is equal to minus E0 over 2, 1 over N sub R plus L plus 1. Okay? And that energy, E0 over 2, has a name. My phone has a first name. It's called the Rydberg energy. And that's equal to 13.6 electron volts. So that's equal to minus the Rydberg over N sub R plus L plus 1.
Are these numbers that we should know? Like you mentioned that we should know that those dimensional analysis tricks, are these numbers that we should know?
Yeah, you know, two numbers you should know. You should know what the Bohr radius is. You should know.
Isn't that a hard trick?
It's high speed.
You should know the factor of 2. Okay, so this is important. This, first of all, there's something we see here that is special for 1 over R potentials. That's not true for arbitrary spherically symmetric potentials. Notice that the energy of the system doesn't depend independently on N sub R and L. It only depends on the sum of them. Any states which have the same sum of these quantum numbers is got exactly the same energy. There is an extra degeneracy in the hydrogen atom. That is not true in general for central potentials. And so what we do is we define what we call the principal quantum number. N as N sub R plus L plus 1. Okay? Or another way of saying it is that N sub R, the number of radial nodes in the wave function, is the principal quantum number minus the angular momentum quantum number minus 1. Okay? And thus we see in this case, we typically would write the, as you know from sophomore physics, the energy levels of hydrogen in terms of the quantum numbers NLN, right? N being the principal quantum number, and in fact, the these are the energy levels of hydrogen have this form. They only depend on the principal quantum number. They don't depend on L or M. Okay? What is the degeneracy in this case? Well,
2n plus 1?
what's that?
2n plus 1?
No, it doesn't work that way. We had the 2L plus 1 for every, so the degeneracy in this case, we'll call that G, is all the different L's that you could have that have the same N. And for every L, we have all the different M's. How many different M sub L's are there?
And it's the 2L plus 1.
Right. Okay. What does L vary over? Well, we have this relationship here. Okay? So, what is the maximum value of L? Given this.
N minus NR minus 1.
Right, so L generally, given n sub r, L is equal to n minus 1, oh, I just worried about that. Minus L, I mean, minus n sub r, right? But what can n sub r, what's the minimum possible value of n sub r? 0. I can have n sub r equals 0. So the L max is n minus 1. That corresponds to n sub r equals 0. Okay? L min is 0, corresponding to n sub r is n minus 1. Okay? All those states have the same total energy. In this state, we have no radial kinetic energy. All of the kinetic energy is angular. Okay? These are what are called circular states, because that corresponds in the classical language to a particle that is going around only with tangential momentum, has no radial momentum. These are the states, these are S states. Those are the head-on collision states where all of the kinetic energy is radial and none of it is angular. Okay, so now this becomes to n minus 1. So, and then we could do that sum. I always forget how you do the sum, but you can do it. You got 1/2 times n plus 1, you know. And this becomes n squared. So that's the degeneracy. One thing to note, of course, is that we've ignored spin. Okay? If we include spin and we don't include any interaction with the spin of the electron, then the degeneracy really is 2 times the spin of the proton plus 1 times 2 times the spin of the electron plus 1 and n squared. Okay? And the spin of the electron is 1/2, so this is 2. And what's the spin of the proton?
Same.
It's also 1/2. So there's really a degeneracy of 4n squared. Okay?
I wasn't, how come you include the spin of the proton? I wasn't, because that.
It's there.
Okay.
In the same way that the electron spin is there. Now we're going to get to the interaction of the spin of the proton with, say, the magnetic field created by the electron. Okay. So that is what we call the hyperfine interaction. Should have studied at some point. And so that, what this tells me, for example, so remember n here, what's the lowest possible value of the principal quantum number?
1.
1. It's not 0, right? Because n sub r can be 0, right? So
Doesn't it come to the fact that degeneracy has to be 1 at the minimum? So if n was 0, there would be g would be 0 as well. Because L and S can both be 0, but n can't be 0.
it comes down to degeneracy. Even if I had no issues of degeneracy, this is just the formula for n. And the lowest value of this is 0, so the lowest possible value of these just can't be negative. So it's really not an issue of degeneracy. It's an issue of this is what n is. Okay? So we have here the states that we call the ground state, which is 1s. Then we have n equals 2. So here's the ionization energy, right? This going down over here, when n equals 1, this is, you know, minus 13.6, or this is, I'll just call this minus 1 revert over here. That's the binding energy of the 1s state. Then I have the 2s state and the 2p state, right? And what are the binding energies of those?
I got 4.
Right. So you go, so it's up here. Already, we're just a quarter. Let's see, this is a half. Yeah, that's right. And that is the 1s state, and I'm sorry, the 2s state and the 2p state. And they're degenerate in this approximation. Okay? And then I have the n equals 3, right? And that's a ninth of a binding energy. And there's the 3s, 3p, 3d. And then each one of these states has degeneracy. Without spin, this has no degeneracy. This has degeneracy none. This has degeneracy 3. None, 3, 5. And then we have spin. Really, there are 4 states here. Okay? And they involve the 4 combinations of spin. We'll see how that plays out in a little bit. Okay? Now, one thing I would mention here is that the, as I said, generally speaking, the different L's are not degenerate. Okay? Generally, the S states will be much more deeply bound than the P states or the D states, because as I said, the S states, you're penetrating. There's something special going on here, and it's a fact of the, if I have a central potential, okay, so let's say I have some, you know, particle moving in a central potential. Generally, what will happen is the orbit will do something like this. It generally won't close on itself. Okay? The fact that it closes on itself for one, so this is when D does not equal 1 over R. When the potential is proportional to 1 over R, then we have this perfectly equal. And there's a vector which is called the lens Rona vector, which represents the some orientation of this orbit, which is conserved. There's another conserved quantity. This is another symmetry of the Hamiltonian. That vector, K, is equal to 1 over twice the mass of vector squared, L cross P plus P, or minus P cross L plus relative position over the magnitude. This commutes with the Hamiltonian. It's an additional symmetry of the problem. And because of that additional symmetry, you can show that there's this extra degeneracy. Remember, symmetry and degeneracy. This is not an accidental degeneracy. This is an essential degeneracy coming from a symmetry. The fact that this thing commutes with the Hamiltonian. It's a separate conserved quantity. That is not true for anything other than 1 over R potential. Okay. All right. Very good. So let's explore a little bit more the nature of the wave functions. Okay? So what we have now are the bound states of hydrogen. The wave functions are specified by these numbers. Now I have my reduced radial wave function. I have to put in my units back. What over R? Yeah, that's good. YLN. Okay. Where my U, we got R bar to the L plus 1. We have e to the kappa minus kappa times R, right? And what is kappa? Kappa is written over there. It's 1 over n. Okay? See it? So that's minus kappa R, but R is 1 over, no, the kappa is 1 over n, times my function here, the function of R bar. All right, so if we go back to our equation, this relates to your point, Z, but what the heck is this damn thing? Isn't this some mathematician's function? We can see that now quickly by if we express, we go back to our equation here for F, and let me write a dimensionless variable X as 2 kappa R bar. Then I get the following equation. X times F double prime plus 2L plus 2 minus X F prime plus N plus 1 plus L F is equal to 0, where the prime is the F dx.
Why is it the cube root of A0? Why isn't it a square root?
No, I'm sorry. This is the square root of A cubed. Right. Pardon me. Yeah. It's got the units of the 1 over the square root of lambda. Pardon me. Right. Okay. So, there's something wrong with the signs here. Excuse me for a moment because I don't trust what is in my notes here. Look at our equation here. That should be a minus. No. Yeah, that's right. Minus 7, minus 1. That's correct. That's what's in there. If I divide by kappa, that's correct. This is the radial. Okay? So this has a form of the following. This has the form of x times y double prime of x plus q plus 1 minus x y prime of x.
Should there be another 2 with that x?
Sorry?
With the x? You just divide by the kappa?
I have to divide by I have to, there's a little bit of algebra here. I gotta put in all, wherever I see an R bar, I gotta put in 1 over 2 kappa x and do that algebra. I believe this is correct. But you just got to go through that. I'm not going to, it's not so important. You just do the algebra. Okay? And this equation is where if Q equals 0, that is Legendre's equation. With the Q not equal to 0, this is the associated Legendre polynomial. So the solution to this is the associated, not Legendre, Laguerre. It's Laguerre. 2 R's in Laguerre?
Does it matter?
Yeah, no it doesn't, but it's Laguerre. Okay, these are the associated Laguerre polynomials. They are, a standard form. The Laguerre polynomial of order n is the associated one with Q equals 0, and they are related to exponential functions. And the associated ones are related to derivatives of this guy. Yes?
So is the Q related to L?
Right, so now let's see what these are.
Okay.
Right? So in this case, what we have, our solution thus, is what? Let's write it on the front board. So what we have here is, according to this, Q is 2L plus 1. Right? And n sub r is n minus L minus 1. So the solution is f of n and L is the associated Laguerre polynomial of order n minus L minus 1 associated with Q is 2L plus 1 evaluated at x, and x is 2 kappa bar, right? And that is putting back in to r over n. So what we have thus is that the wave functions associated with hydrogen are equal to, putting it all together, r over a naught to the L, 1 over a naught to the 3 halves, e to the minus r over a naught n. The associated Laguerre polynomial for that radial nodes associated L plus 1 to r over a naught n times the y Lm. Okay. Again, when doing calculations, it always makes sense to work with dimensionless units. You know, you have to carry around all the A naughts in here, right? This would be R bar, R bar, R bar. Everything is dimensionless. And then at the end of the day, you put the dimensions back, like we did for the harmonic oscillator last semester. Okay? All right, let me just quickly show, just to get some feeling for things, what, I'll grab it.
There's certainly a reason why we can't develop something like this for any of for nuclear materials. Like imagine trying to do it for, what is it, like that little piece of the periodic table that's down on the bottom, they're all like in the hundreds of pages trapped into the end of it.
All right, sorry folks, let's hope this works. If not, I'll give up. So what I wanted to do is just show you what these wave functions look like. All right. Come on. All right. So these are plots of the on the right here is the full radial wave function squared, or no, not squared, just the radial wave function as a function of r in units of a. What's plotted on this side is the reduced radial wave function squared. Why is that something which is useful to look at? Well, you remember, let me put the lights back on for a moment and we'll come back. Remember that the full radial wave function is the reduced radial wave function divided by r. Okay? Now, the probability to be in a certain RDR is equal to the square of the wave function times r squared dr, right? Because you have a spherical shell whose area is growing like r squared. So this is the reduced squared. So the reduced radial wave function squared tells you the probability density to be in a spherical shell around r. And so that's what we would typically plot. Even though the probability amplitude is peaked right on top of the proton, the probability to find the electron at the position of the proton within a limit of the r is 0 because there's no volume there, right? So it goes to 0. And it's the peak probability sits actually exactly at 1 Bohr radius away. The mean position is a little bit, or the mean rate is a little bit bigger. This is the 1s state, okay? The 2s state looks like this. How many nodes does it have? Well, it has n is 1, L is 0, n sub r is n minus 1 minus L, right? So n sub r is 1. So it's one node, and there it is. Right? Takes a little while to get. And this is the probability distribution of where the electron is relative to the proton at the origin.
Does it go to 0 there? The probability go to 0 right after that? Are there, like, how many different places does the probability go to 0?
Exactly here and here.
Okay, so-
And then it asymptotically goes
Okay,
to
so,
0.
okay.
It's actually, this is the exponential fall off,
Okay.
right? Remember, this is the radial distribution. The angular distribution is defined by the spherical harmonics, right? So for an S state, L equals 0, what does the angular distribution look like? It's sphere. It's complete. There's no difference in probability of being any direction relative to the sphere. So this is like a cusp that's spherically symmetric, right? That's what this wave function looks like. And then these guys, well, it's hard to kind of imagine. It's angularly, it looks like, in this case, well, it depends what the value of m is, right? There's y, l, m. This is what the radial distribution is. All right, good. In doing any kind of calculation, atomic physics calculation, it all comes down to calculating things about the radial distribution, the expectation values of the radial coordinates. The angular ones are easy to deal with, as we will see. But it's the radial ones that are kind of a pain. And I'll give you some of that pain in homework. But there's one trick, which I learned as an undergraduate, which is really neat, and I want to share it with you. So often we care about some expectation value of some observable. Okay. In one of the stationary states. Now, we can get at this by a trick sometimes. And the trick is a trick that was due to Feynman and Hellman. It's called just the Feynman-Hellman method. And the trick is the following. Let's write the Hamiltonian of the system as a function of the charge of the electron, the mass of the electron, and L. Okay, that is this guy. There it is. P sub r squared over twice the mass of the electron plus h bar squared L plus 1, 2m r squared minus d squared for r. Okay?
And by m here, you mean the mass?
Yes, excuse me. Here's this indeed. Thank you. Let me emphasize that by calling m sub e. It's the mass of the electron. Thank you. I got that confused. All right. All right. So now if I look at the expected value of the Hamiltonian, let me call all these parameters, this parameter C. They're one of those parameters. This is M sub L. This is some energy, N, well, actually it only depends on N, C, is equal to, in our case, for the bound states, that's the Rydberg, it's a Hartree over 2 times 1 over n squared. And n squared is n sub r plus L plus 1 squared. Okay? So now here's a trick. The trick is that we are just mathematically, this is a continuous function of these parameters. It's a continuous function of the mass of the electron, the charge of the electron, and L, and n sub r, right? I mean, they're numbers, but mathematically, this is just an equation. And so I can take partial derivatives. So if I look at the partial derivative of the energy, I'll write it out explicitly in terms of n sub r and L with respect to one of these parameters, that's equivalent to taking this. Let's try it. So, for example, let's let C be L. Then, when I take the partial derivative of my Hamiltonian with respect to that, right? Oh yeah, so that's L squared plus, yeah, okay, thanks. 2L plus 1, h bar squared, over twice the mass of the electron, times 1 over r squared. Okay? So that tells me that the expected value of 1 over r squared in a stationary state is equal to the partial derivative of the energy with respect to L by this formula. And so I plug that in, and I get 1 over a naught squared n cubed L plus a half. That is slick. It says I don't have to go through and look at some recursion relation for the Laguerre polynomials and the generating functions and do some integrals with integration by parts 5 times. You'll get to do that, don't worry. But for certain ones, I can just write down the answer. It's such a, I mean, God, that funny movie. It's my new sitcom. So there's some other examples of that in the notes. You can take a look. And these are useful expectations. We'll see. We're going to do the fine structure of hydrogen and perturbation theory. We need to know what this damn matrix element is, and calculating it is annoying, but I guess we get it like that. So you'll have other examples like that in your homework. All right? Okay, folks. Very good. Have a good rest of your